Okay, so I was cautioned that I should maybe remind people, yeah, so that I should not start my talk with I will use all the concepts and results from Swan's talk 2 months ago on Nori motives over field. So I will not do that. So maybe just let's talk before I talk about relative Nori motifs. I just want to talk about motifs in general. So I think half the room is are experts on motifs, and the other half don't know motifs at all. So it should be fun. Okay, so what is supposed to be so I'm going to fix as a nice scheme. Very soon S is just going to be an algebraic variety over a field of characteristic 0. And what are relative motifs over S? So you have schemes over S. Okay. And you think so on this category of schemes over S, you have a theory of relative cohomology. So if S is like the spectrum of a field, schemes over S would just be like schemes over a field. And you have this theory of like Vel cohomology, or mixed Vel cohomology, I should say, like Betti cohomology. If S is spec C, you have Eladic cohomology and all that. So you this, I think there are categories of coefficients. Yeah, so if S is a general scheme, so these are basically categories of sheaves over S that are supposed to express the relative cohomology of a scheme over S. So, for example, you could take Betty sheaves. Betty sheaves on the C points of S is if S is a scheme in characteristic 0, if S is a scheme over C, for example. Or you could take Eladic sheaves over S if L is invertible on S, or you could take mixed point models. Again, if S is the scheme over a subfield of C. Okay, so is it clear that not everything I write makes sense for every S? Okay, and then, so if S is, for example, let's say S is spec Q. Ah, I see. So you have this category of like schemes, so nice schemes on Q, and then you have this cohomology accomplished. So for example, Betti cohomology that goes into Q vector spaces. You have gram cohomology that also goes into filtered Q vector spaces. And you have Eladic cohomology that goes into Eladic representations of the absolute gamma group. Okay, and you have all these comparison isomorphisms between these cohomologies. For example, these two become isomorphic once you extend the scalars to C. This one is if you extend the scalars to QL. This one is isomorphic to this one if you forget the action of the Galois group and all that. Okay, so this now if S is a and if S is a I don't know a finite field, then forget these two, but you still have all these Eladic cohomologies, and there are conjectural comparison isomorphisms. And so the theory of motifs is supposed to kind of explain these comparison isomorphisms and be something that lives here. So universal cohomology theory. So maybe where's the eraser? Please don't tell me that's the eraser. Yes. Oh my god, how do I use this? Oh, that okay. It's okay. Okay. So motifs, they are supposed to live here. So you're supposed to have this abelian category of mixed motifs, some kind of universal cohomology, and then this become what we call the alienation factors. Um, so now it's that. Yeah, that's a few factors. And you're supposed to recover the cohomology series by this process. Okay, so I was talking about mixed models, so mixed model, sorry, right? So here, instead of categories like Q vector spaces, you have like, well, Q vector spaces varying over S, so sheaves of Q vector spaces, sheaves of like analytic sheaves of S and all that. And so I guess the wish is that there should be here a category. Okay. Um, here, this is should be the category is mixed models over S. Now it's a median. And it's supposed to have a bunch of properties that I'm going to recall now. Okay. And then when you compose this, right. Such this. So if I have X over S, I'll send it to yeah. I'm just hesitating between taking just HN or taking H star. It doesn't really matter. So let's call this S F. Then you get some motive. HN of X and S. And then if you apply the realization, then you're supposed to get Rn F lone star of the constant object and X, whatever it is. Now, let's talk about the ideal picture. And then I will tell you what is known of the ideal picture. Okay. So these motifs, by the way, so you could think about them as, I guess, two kind of equivalent ways. So one way is this is a kind of a linearization of this category of schemes. So you have schemes, they are complicated. You have all this invariants that are like linear algebra objects, and this universal invariant is like the universal way to make a scheme into a linear algebra object. Yeah, actually, yeah, it's no, it's not. Sorry. And another way to think about it is the way I was talking about this, like it's a universal cohomology series or it's a universal category of coefficients. And nobody corrected me, but here, these were all triangulated categories, so I guess I should make this a triangulated category. And the one that is abelian is just this one here. Okay. So the ideal picture is that for every S, so we have this an abelian category of mixed motifs over S. Let's call it M of S, and this is a really small board. And then you have a bunch of extra structures. So the first thing is, so I'm told that you guys are familiar with six-functor formalisms. So the first thing we want is a six-functor formalism. Was this? So was there? Well, S varies. So what does that mean? It means if you have a morphism of schemes, you should have this pairs of adjoint functions, F upper star, F lower star, then F lower street, F upper street. So this is for F morphism. And then you should have tensor product, which is left in the internal hall. And then a bunch of compatibilities. I'm not going to define a six-functor formalism here, but like base change, projection formula, and things like that. And this is on the derived categories because, well, if you have a sheaf, for example, on S and you apply the direct image functor and the correct object is the derived direct image functor, you're going to get a complex of sheaves and not just a sheaf. Okay, the second thing is you want a theory of weights. So like objects of this MS should have weight filtration. I'm already betraying, by the way, that this I'm going to be reverse relative motives when I said that. That doesn't work so well actually. It works well for like 10 seconds. So. Is there a trick to using this? Oh, God.
You need to try to look for a bigger one. You have to look for a bigger one. Maybe the German system has its merits. Maybe the German system has its merits.
Yeah, no, the German system is great. So, yeah, I'm not going to read the full formalism. The idea is if you've seen weights for mixed function modules, it should work in the same way. Or if you've seen weights for analytic sheaves on like for varieties of finite fields, it should also work in the same way, except for analytic sheaves, we don't have this pure object class anything. Or another way to say that is there could be a Bondako weight.
I like this one best, but
yeah. So if you like Bondako weight structures, there should be a Bondako weight structure on this graph category. That is transversal with the T structure, the canonical T structure. And the third thing is like so the Tanakian-ness that I almost wrote it, but it wasn't quite true. It's not true for MS, but there's a if S is fused or if S is regular. There's a full subcategory of these objects. I don't know. As selected. So if you're over a field, every object is this. Okay, so this is what we would use to define motivic Galois groups, for example. And the fourth thing is a relationship with algebraic cycles. So maybe I write it in a very big way, like Hans in this DBMS to be connected to algebraic cycles. And at the very least, algebraic cycles should act on these objects, or algebraic cycle on S cross T should give you on X. An algebraic cycle on the product should give you a morphism between the motifs of the two factors. So that is like the dream. What is the reality? We have nothing of that.
The bigger one, you can try to erase.
Huh? Yeah. I will. So the reality is we don't know how to do this. Thanks for joining to my talk. So the reality, so we have this okay. So we have these categories. So I'm going to call this DLC. So this is a constructible geometric or whatever. Voivodski motives. We have this D and C. So this is constructible Nori motives. And then we have this realization into categories of coefficients. Okay, and these are triangulated categories or stable infinity categories, if that's your term. Okay, and okay, so what do they satisfy? So let's should I do a little? Okay, so six-factor formalism. Yeah. So this is kind of a comparison. Wait. Yeah. Well, okay. There is like an elephant in the room that I guess I will get to at the end. That I wrote triangulated categories and I didn't write derived category and I didn't category. So for weights, for example, it should be expressed as there is a Bondako weight structure on this category. Tanakiness, nice category of these objects. Yeah. So Nori, yeah, and this, I mean, yeah, kind of. Yeah, there's a nice category.
For which we have rational motives.
Yeah. So I'm rational during the whole talk here. I mean, I'm going to say, yeah, you have a nice category of these objects. Yeah. Everything is rational. I will not say it. Relationship with cycles. Yeah, no. And the last one, bonus. So which one is actually a derived category? So I'm going to call this T structure. Okay. So T structure, is there anybody in the room who doesn't know what a T structure is? Is there anybody who dares admit that they don't know what it? So yeah, basically what this is asking is this the derived category of something? And the answer is actually this doesn't mean no, it means unknown. Okay. Because conjecturally these are equivalent. And conjecturally everything is beautiful. Okay. So now maybe I should tell you
Maybe a question.
yes.
So I've heard this difference many times, but I'm curious, what is one thing that would give having an obedient category rather than just a derived category?
You mean for Voivodski motifs?
In general, like let's say what was the motive. Let's say if we
I mean,
that it was an obedient category.
So for Nori motifs, there is an obedient category. Right. So okay, but basically, if you have an abelian category of Voivodski motifs, such that this realization function is exact for the perversity structure here, then these categories are equivalent. This is a result of my students' one. So, and what you would need for that, for example, over a field, is the standard conjectures plus epsilon. So it's pretty big conjecture. If you have an abelian category, that implies the standard conjectures. Yeah, so it's the situation is not perfect, but I guess we have all the properties. It's just not the same category that has the different properties. And I should say, well, maybe I won't write it. So this comparison function that's supposed to be an equivalence. When do we actually know it's an equivalence? On zero motifs, I think that's all. There are some results on one motifs. over a field, or for the effective motifs, we know that one motifs are equivalent here and here, but we don't know it in the non-effective case. Okay, so the biggest, I should say, the really, this, I'm kind of glossing over it, but this is a really big problem in Nori motifs that you really do not know how to calculate extension groups. And maybe you will understand why if I show you the definition. Oh, so maybe I should give some definitions. Right. Okay. Although I've been told that most of you are familiar with Voivodski motifs, so maybe I should just recall quickly what the definition is. It's pretty simple. All the definitions are pretty simple. So how do you make Voivodski motifs over S? Okay, so let's see if I said it's simple, so if I make a mistake now, I'm going to look stupid. Roughly. So these are rational Voivodski motifs. So you take the category of sheaves for the entire topology on the category of smooth schemes over S. Okay? And then you take the derived category of that. Okay? And then, so in that you have a functor from smooth schemes that is supposed to be sending a scheme to its homological motif. So you send X to, so what you're going to take, take the pre-sheaf T goes to Q of, well, I'm not sure. So this is the free Q vector space on this Hom set. And then you sheafify it. Okay. So then you do what is called the A1 localization, I think. A1 localization. So what is A1 localization? That means that you know it. So every time you have an X, so you have a. So this is the covariant functor. Every time you have an X, well, you have a projection from A1 over X to X, so you apply M, and you want this to be invertible, because basically you want X and A1 cross X to have the same cohomology or homology. And then you do what is called P1 stabilization. Okay. What is P1 stabilization? So you make the tensor product. So this category has a tensor product. That's just the usual tensor product of sheaves. And I should have said rational. And just believe me that the tensor product is just going through all these things. So you make tensor product by T invertible. And where T is the state motif, so T is the motif of T1 over S modulo the motif of the point at infinity. So it's basically a Q of 1. Okay. So of course, like I'm sweeping a lot of things under the rug here, because if you want to do things correctly, you don't take this triangulated category and do this. I mean, you have to work with the model categories, the right model structure, make boost field localizations and things like that. And these are supposed to be like spectra, T spectra. Okay. But the idea is basically this. Okay, and then you get a category that you call, I don't know, Dn of S, which is the category, the big category of Voivodski motifs. It comes with the tensor product. it comes with this unit object, which is the M of S. And DMC of S is a subcategory of compact objects. Okay. And this one, okay. So I just realized that maybe I should have mentioned, maybe I can mention now that all these properties have been proved by people. One of these persons is in the room. So the definition is due to Wygotsky. I think it probably at least inspired probably by Fabien Morel's from like stable homotopy category of schemes. And the proofs of all these properties are due to a loop and systemistic in this independently. But yeah.
Just a question, by compact objects, you mean the bounded ones? Or what do you mean?
What does bounded mean?
I mean, there are complexes.
They are not really complex. I mean, okay. No, I mean that the harm from the object commutes with filtered coordinates. So there's a general, but you can think of them as also constructible objects, but I will need to define constructible. But
okay.
yeah, I mean, okay. Also, this is a category with a tensor product, so there is a notion of dualizable object, and constructible means becomes dualizable on the stratification. So actually, the fact that these are equivalent conditions is not obvious, but over the schemes that we will consider, I think it's due to Szyczynski and Deglis, right? Okay. Sorry. Yeah. And then also, so I guess I didn't put here in the list of desiderata that there are realization functors because, well, this is I have already erased them, but this is true for all the categories that we have. So you have the realizations. But again, et al. At least. The realization of mixed function modules took a little more time. Maybe I can talk about it at the end. So these are also due to the same people.
Question.
Yes.
So is T supposed to be the thing corresponds to the Lefschetz motive? Or
this T, yeah, it's the Lefschetz motive if you want. Yeah.
Okay.
So tensoring by T is state twist. So T twist is tensor product by T.
We were sheet.
Yes. Yeah, so we are in homological convention, so I'm never sure. Yes, thank you. Okay, so this is Wygotsky motif. So this definition is pretty simple. Why this is a reasonable thing is maybe less simple. It's a reasonable thing because it has all these properties that I'm going to erase now. Well, maybe I should say over a field, there is an even simpler definition where it really looks like you take the category of smooth varieties over the field. The morphisms are finite correspondences, and you kind of like forcibly linearize it and force these properties. And you force Mayer-Vittoric. I mean, in this case, Mayer-Vittoric comes for free. Okay, but the main focus is supposed to be Nori motifs. So how about Nori motifs? How do you define that? And apparently I looked last week and he did not give his definition of Nori motifs, which is a shame because I'm also not going to give his definition. I'm going to give Nori's definition and then Igora's definition. Okay. So Nori's definition you have already seen, but I am told it's a good idea to recall things. So Wygotsky motifs is kind of, I told you there are two ways to think about motifs. So linearizing the category of schemes. and by maybe forcing a few things to be true that you want to be true in cohomology series. So this is the Wodowski approach. And Nori is more of a universal cohomology theory approach. Oh, and I'm sorry, so this was not intentional, but I realized I forgot a big restriction to Nori was just like it only work in characteristic 0. I should have put it in my next table that I raised. Because this is, for me, is probably the biggest drawback of Nori models. So let's go in a simple case. So I'm going to take K, a subfield of C. I'm sorry. I know. Great. Yeah, but it's like this fancy Japanese student do that. But yeah. Okay. So this is you don't actually need to be on the subfield of C, but this makes it simpler to give the basic definition. Okay. So what is the idea of Nori motifs? We are going to do Nori motifs of K. Okay. So did I have some great idea about how to? Yeah. No. Okay. So the idea, you're going to look at this. Okay. So let's start with a little bit of vocabulary. So in Nori motifs talk, the diagram means oriented graph, which you might also know as a quiver. And then if you have D is a diagram, and C is a category. So a representation. E means morphism of oriented graphs. Morphism of diagrams. Right, so a category can be seen as an oriented graph, just forget composition and forget the identities. And so morphism of oriented graph is just something that sends vertices to vertices and sends arrows to arrows respecting source and target. Okay. And so the idea of Nori motifs is that we start with this diagram dk. So dk is going to have vertices over triples x, y, and n. X is a variety over k. Y is a closed subset. So I write closed subsets like this. And n is an integer. And then arrows. If you have two types of arrows, you have functionality arrows. So if you have morphism of varieties from x prime to x, that sends y prime to y. It gives you an arrow in the other direction. So note the n here is the same. And then you have this connection arrows. Wait, I'm going to get it in the wrong direction. That's why I have notes. So connection arrows. Here. Right. Y, Z, N to X, Y, and this one. So your Y is a closed subset of X, Z is a closed subset of Y.
So is it Y any equals subscheme or just the subvariety?
It doesn't matter.
Okay.
Because you're going to take a homology which doesn't see nilpotence. So you can just take a closed subvariety. And then you have a representation. So representation from dk to vector spaces. It sends x about n to representative homology of the sequence. These coefficients, I'm going to take coefficients in Q, make my life simpler. Okay, and what does it do on the arrows? Well, cohomology is contravariate. So, I mean, if you have an arrow from x prime to x, you have an arrow between the cohomology groups in the other direction. Okay, and then you can extend that to relative cohomology, and then this is like the long. This is the connecting arrow in the long exact sequence of relative cohomology. So normally one should have explained all that, so that's why I'm doing a bit more quickly. And then Nori says, well, the category of Nori motifs is going to be the universal Abelian category by which these factors. Okay, so I guess the definition, well, it's actually the category of effective Nori motifs. So this is the universal for which I. So here there is a statement that such a universal Abelian category exists. So maybe I think Swan talked about that, but I'll come back to it later because it's actually important. But let me maybe proceed a little bit. So this is effective motives. Okay, so then you have to define. So I'm doing a speed run of Nori motives of the page here. Yeah, so you have to define tensor product. The tensor product. So the idea is that you're going to say that the tensor product of two of these. Well, it should be. So you want to define tensor products so that the QNet formula is true. And of course, this is not the QNet formula. Uh, okay. Again, because Swan already explained this, let me just maybe. So I wrote a few formulas that me say in words what is going on. So what is going on is that so if you have triples x, y, n and x prime, y prime, n prime that satisfy this property, so the cohomology is concentrated in the relative cohomology is concentrated in 1 degree, which happens to be the degree that I picked here. Then the QNet formula tells you that this triple here will have cohomology concentrated in degree n plus n prime, and that will just be the tensor product of this. So in that case, the tensor product on the category of Nori motifs should just be given by this on the diagram. And then you have to, there is this thing called the basic lemma that will tell you that objects satisfying this property actually generate the whole category. Okay, so that you could define the category using the sub-diagram of objects satisfying this property, and you would get the same category.
The Bayesian construction. Is the Bayesian construction?
So the basic lemma is a particular case of Berlinson's lemma. But it was proved independently. I think it was proved independently at least 3 times. Once by Berlinson, once by Nori, and once by Villon. Yeah, but Nori calls it the basic lemma, and Berlinson calls it lemma 3.2 or lemma 3.3. Yeah. In his paper on derived categories of progressives. Okay. And then, yeah, so the actual category of Nori motifs, it's so you take NF, and then you make tensor product So you have to make tensor product by the Lefschetz motive in virtual. And what is the Lefschetz motive? Well, you can define it. Well, for example, you can take H2 of T1. Or you could take H1 of GM. Yeah, so here I've been a little bit careless because normally, so it's not H. I should give another name to the functor into affecting Nori groups.
I noticed that here is kind of unpointed T1 is T1 empty.
Yeah, I mean, it doesn't matter because you're only taking H2. So the reason you pointed it, if you're doing Voivodski motifs, you are triangulated, so you get the whole homology complex or homology complex. So you have to get rid of the H0. But the Nori thing, you see X, Y, N goes to HN. So you're kind of forcing the HNs to be separated in your category. I mean, I can put infinity here if it makes you feel better, but it won't change the results. Right. And yeah, so that's basically so that's Nori motif. So here I should say, so note that this inclusion here, this inclusion into cube vector spaces, this is basically the Betti realization function on Nori motifs. So this real D8 extends to the full category, to the category of possibly non-effective Nori motifs. Okay. And now maybe I should talk about the other realization functions. Well, maybe not really. Actually, what I can talk about is yeah, I just write it here. The theorem, let's say, Nori never actually wrote a published paper, so the construction was kind of I don't know. This is like notes going from people to people until these two people wrote this big book about periods and Nori motifs, which is now the reference for Nori motifs of the field. And then, which he also never published his results, unfortunately. So Anki is an Anki category. Weights its lists. And there's a function from what was motifs. This the factory preventing realization. The I don't remember where it was before. So I said I was going to talk more about Nori's universal category.
Good question. So where did the materialization come from here for Nori motifs? Is it just H1? Or
It's just so Nori motifs is it's defined as a non-full subcategory of Q vector spaces. The Betty realization is just inclusion in Q vector spaces, because that's, I mean, so Nori motifs are defined as like the universal factorization of the Betty realization. So maybe here I should write all the realization synthesis. So you can prove that L-adic realization, Hodge realization exists, but I think this construction is not the best way to do it. But so if I have time, I'll say more about how you construct the other realizations. Right. Yeah, so I have this universal abelian category to which these representation factors. So maybe I should tell you about that. Okay, what is the theorem? So you take so do a diagram. A and abelian category. And T is a representation. And then we define factorization of T. So this is well, it's okay. So the problem with the word diagram is that it means several things. I wanted to write diagram, but so factorization of T is this data. So here it should be a representation. This is another abelian category. And this F is a faithful exact function plus the data of an isomorphism between T and F composed with U. So here I'm being possibly unnecessarily careful because I'm not formalizing things in a lot of references. This is written as an equality, but of course it is not. So, but yeah, morally, a factorization of T is just a factorization through an abelian subcategory of A. Okay, and maybe while I erase, I can tell you, so these factorizations form a category, right? So I can let you imagine what a morphism of factorization is. Do I need to tell you what a morphism of factorization is, or actually I don't want to tell you? I mean, it's an essentially commutative diagram of functors, but you have to keep track of the isomorphisms so that they're all compatible. It's very easy to write out. And the theorem so the category of factorizations has an initial object. I usually write it like that, although it's not. It's not standardized, so this R is supposed to mean realization, and T bar is because I have no imagination. Okay, so that's Nori's. So this initial object is what I call the universal factorization before. Okay, so why do we give several attributions? So this theorem is very strange, but it went through several cycles. So Nori states it and proves it in the case where A is the category of finite dimensional C vector spaces. Yeah, C, but okay, it works. I mean, there are some nodes where they make it work, or the category of finitely presented modules over an Ethereum ring, for example. And he has some kind of little bit ad hoc proof. And then there's, well, several people like Ivora proved a more general version, Arapura proved a more general version. And then these guys are very Viale and Prest proved it in the case of a general ability category. And the proof is kind of so trivial that you are very surprised that nobody has seen it before. So maybe that the proof. The idea of proof. Okay, so you have this diagram D, and you just go through. Well, so you take D. Okay, maybe I will make a bigger board. Proofing features. Okay, you have D and you have A. You have T. So the first thing is you make D into a category. Okay, so how do you do that? You take. So this is the past category. So this is the universal, well, the free category of D. So the objects are the vertices of D, and the arrows are the paths in D, and composition is concatenation. And every functor extends, every representation extends to a functor in actually a unique way. Okay, then you want to make this path category into an abelian category. So the first thing is you are going to make it into an additive category. Okay, so I usually do that in 2 steps, but so you have this pre-additive category. So it's just you take a path category and you just linearize it. So you replace the harms by the free abelian groups over the harms. And just extend composition, you define it by linearity. Okay, and this extends again in a unique way. And so this is a category where the harms are abelian groups and composition is bilinear. And then you want to make this into an additive category. So what you are missing is direct sums. So you just formally add direct sums. So you formally add finite direct sums. The harms are just matrices of harms here, and composition is the matrix product. Okay, and here again, so this extends. So here I should say it extends uniquely to the additive functor. This extends to an additive functor. It's unique. So, I mean, here you start getting into 2 universal properties. The extension is only unique up to isomorphism because you have to choose direct sums here. Maybe I will ignore these problems. Okay, so this is an additive category. Now you want to make it into an abelian category. So you take the abelian envelope. What do I use? Let's call it really, because everything is called A. So this is the freight abelian envelope. I'm going to tell you maybe in a second what is the abelian envelope. Well, so the abelian envelope, that's an abelian category with the universal property that every additive functor extends essentially uniquely to an exact functor. And you get it. Rough ideas, you formally add kernels and co-kernels. It's a little bit more complicated. It's actually the most complicated construction here, which is why I'm not giving it. But yeah, and then how do you define Q of t? Well, the only thing that is missing here is that this function is exact, but it's not facial. So you just make it facial. So you take this like horrible thing. And you portion it like the kernel. Okay, so you know. And the universal property just comes from all the universal properties of all these constructions. And I don't know. It's one of this, like if you see Ibora's proof, you know, it's very amusing that this simple construction was missed for so many. Okay, so this is Nori's universal category. Okay, so how long have we been talking? Oh, 1 hour. Great. Now I can finally get to the relatives. Okay. So far, I have just completed Swanstone definition.
Yeah, it's one of curiosity. So the isomorphism between image and co-image is it simple or is it as complicated as updating formally kernels and co-kernel?
Here? Sorry, what do you mean?
But isn't there like don't we need also the isomorphism between image and co-image?
Yeah. So the way you construct this abelian envelope is you make it you construct it inside the category of additive functors from your additive category to abelian groups. So you construct it as a subcategory of a category that is already abelian. So the isomorphism between image and co-image just comes for free. I mean, okay, so it's a bit more complicated because you have to do it in 2 steps. So so to add co-kernels, you take your additive category, you take additive functors from this additive category to abelian groups. You look at the functors that are co-kernels of representable functors. And this is your like co-kernel closure. And then you add kernels by a dual process. So you're like additive functors over additive functors over this. But yeah, so I guess the answer is that this isomorphism comes for free.
When will this be adopted?
Hmm?
When will this be adopted?
So I have a formalization, but it's not phrase construction, it's Adelman's construction, which is a bit different. I'm just too lazy to do PR it. Next week, if you want to PR it for me.
Yeah, maybe.
But the Nori construction, yeah, I'm supposed to write my mind. I mean, it's formalized, yes. Like the last missing ingredient was that this quotient is an abelian category, but Joel put it in mass label, I think. So. Right. Well, maybe I should should make a remark, and I erased the. And this is actually a pretty crucial remark. Yeah, is that so I mentioned there is this Harrer theorem. Right, this realization function. And as a consequence of that, is that actually instead of using this category of this diagram of triples to define Nori motifs, so we can define Nori motifs as the universal factorization of this function. Well, okay. So here you have dB of 3 vector space. And here you have like the Betti realization. Okay. So basically, what I almost wrote, which would have been not have made any sense, is that I just like this functor, I take H0 and I take the universal realization of factorization of that. It would not have made sense because I would have used Nori motifs to construct Nori motifs. So what you want to do is you take the composition, which is Betti realization on frequency motifs. This runs into complexes of 2 vector spaces. You take H0, this runs into 2 vector spaces, and you take the universal factorization of that. And this is Nori motifs, and the advantage is that you get Nori, you don't need to invert the tape motif or anything. You just get this category of Nori motifs directly. The drawback is that this is a more complicated construction because you're using Volvoski motifs instead of just very basic things. So, relative views. Okay, so in the relative case, yeah.
It's only works in characteristic zero.
Yeah, because you're using the Betty realization.
Okay, but there's no approach to try to do this for characteristic P?
Yeah, I mean, so the problem characteristic P, you can probably make it work in characteristic P. The problem is in characteristic zero, you have the Betty realization and you have comparison isomorphisms between it and all the other classical realizations. So you will get one category of the category of Nori motifs for the Betty realization is actually the same as the category of Nori motifs for any Aladic realization. So in the classical approach of Nori or Huber Munestack, they are equivalent categories. If you take this approach, they are actually the same category. Because in this approach, this construction simplifies a little bit. And then, I mean, you end up with. Actually, what am I saying? Even if you take this proof of Nori's factorization, the only thing you need to prove is that the kernel here is the same for every realization. Yeah. And I haven't tried to do it in this setup, but if you start from this, then it's easy to prove the kernel is the same using the comparison isomorphism. So so you get the same category for each realization. If you do it in characteristic P, you have to just you use the Aladic realization. I don't know. You use the 3-adic realization, you get a category. You use the 5-adic realization, you get another category, and you don't know how to compare them. So the construction works, but it's less interesting. And the other thing you lose, so you still have the theory of weights, but you lose the fact that your objects are semi-simple, or you don't know how to prove it because the proof in characteristic zero uses the Hodge realization. So it uses Hodge theory. Yeah. So I guess it's a little bit. So it's not that Nori motifs don't exist in characteristic P, it's that the too many categories of Nori motifs exist in characteristic P. Okay. So the relative case, yeah, was.
Oh, yeah. It's boring, but yeah, the other. If the boundary original one is monodal, the factorization is also.
Yeah. So if you want to, yeah, sure. You have enhanced versions for tensor products that I didn't want to state because they are more complicated. But of course, you want a tensor product from this category. So here, well, so the answer is yes. Yeah, I'm a bit scared of tensor products because of sign problems. Yeah. So the relative case, there is a little game. So, well, the first thing in the relative case, first idea is so use the relative type like the relative Nori diagram. So that would be a scheme over S. So now we fix a base scheme like, I don't know, S over K. Let's say an identity. And K is still a characteristic zero field. Actually, a subfield of C. Okay, so relative. So you could just take the same category, but now all the diagrams are just schemes of S. Yeah, and then define some relative cohomology. And then the universal factorization. Okay, this is actually the first two definitions of writing Nori motifs by Arthur and Nori use this point of view. So the difference between these definitions is that Arapura uses usual relative cohomology and Evora uses perverse relative cohomology. I don't want to write the formulas because that's not the definition I want to use. And so why is that not the definition I want to use? Actually, I tried to work with this definition for a while. It's a perfectly nice definition. I mean, you can do some things with it. So the thing is, in the relative case, we don't just want to define motives over S. We want to define the operations. Okay? So the operations, so the thing with this universal Nori categories.
So for you, no, that's not.
Yeah.
For you, I see the scheme over okay, characteristic zero.
Yeah, characteristic zero. Yeah. Because I always use Betty realizations to define these things. Yeah. Is the notation problem?
And you want that the close immersion. So the close immersion is over S. Okay, that.
I mean,
something.
No, just a closed subscheme. Yeah. And so I mean the trick is that if it's a closed subscheme, I can see it as an S scheme via the morphism from X to S, and then this becomes an S morphism, of course.
Yeah, of course.
Yeah.
It goes just fastness.
Yeah. Right. So yeah. So the Dori universal thing. So one thing you need to. So when we start doing this, trying to define these sheaf operations, we have to ask ourselves, how do we define functors on these Nori universal categories? Okay, well, they have a universal property, okay, which is here. So the idea, maybe I don't erase the universal property yet. So how do we define a functor on this? How do you define a functor on this that is not just going through this, of course? And there is one way to do it, is you have to define, well, okay.
Sorry, but
yeah.
Perhaps it's a topical question.
Yes.
So you don't ask that why is flat over S or something? No.
Well, okay, so I mean, this is really not the definition I want to use, so I don't care. Yeah.
Okay, I understand.
I mean, Arapura puts some conditions on why to make his constructions work, but this is, I mean, yeah, I'm trying to explain that this is not the right definition. Yeah. But I mean, even if you ask that it's flat, you're just going to make your life more complicated. Yeah, at least. I mean, you don't ask that X is flat. You don't ask anything about X.
Yeah, that's true. Yeah.
Arthur, it's very complicated. No, Evora doesn't. But yeah. So to define a functor on this, so basically, you have to use the universal property. So the universal property tells you that if you have another factorization of your T, maybe I can write it. This is just factorization of T, then there exists here an exact factory. Essentially unique. Okay. And then you can extend it a little bit to maybe functors that are not factorization. So maybe you also have another diagram and another representation, and you have something exact here. And the thing commutes. Okay, so let me just here. Okay, so on the proof, the modern proof that I gave of Nori's factorization, it's pretty easy to show that the factorization is actually functorial in the representation. So, but this has to be an exact functor. Okay. So I guess this is probably the most important point I should make today is that if you want to construct a functor on this universal factorization, you need two things. You need it to be defined at the level of the diagram that you're using, and you need it to be exact on the realization, whatever realization you're using. Okay. So, for example, in the Arapura setup, pullbacks are very easy to define because pullbacks on the level of diagrams are just fiber products, and pullbacks, heat-x reactive cohomology pullbacks are exact. Okay, but push forwards very difficult. Okay, now if you use this, well, pullbacks will be easy to define, but something like nearby cycles, not so clear. Okay, so our first idea with Evora is we use Podolsky motifs as a type of. Why? Well, more directions. Okay, so so basically I spent a few months fighting with this diagram, and at the end I said, yeah, why don't I use Podolsky motifs? Because over here we know this gives the same result. We know this should give the same result, even over S, but here you already have the 6 operations. So your life is simpler. Okay, now second thing. Which cohomology? Which representation? So maybe here is a thing for you. So you have to choose a representation. So you have your Podolsky motifs. Yeah, it's good. I won't have time to get into the really technical stuff, which is awful.
Now you're not anymore in characteristic 0.
No, I'm in characteristic 0. I'm always in characteristic 0.
Sorry.
Yeah. Because I'm going to write right now Betty realization. Right? So our Betty. Okay, so you have, just like in this characters, and just like in the kids of the field, you start with Betty realization, and then you want to go into an abelian category. So you have two choices. Well, okay, you have more than two choices, but you have two main choices. First choice is to go into the category of constructible cubes. So you use like H0, right? Or second choice, reverse cubes. You use a reverse cube.
That's sorry, just understand it. But if suppose that I forget everything what you said
Yes.
afternoon, right?
Yeah.
And I see this.
When did I say it? Yeah.
Yes. So now S can be any.
But I wrote that.
No. It can be. Okay, I
Yeah.
look at the first, and then I can have other realization.
Yes.
Okay.
But I told you, no motifs, they totally exist in characteristic P. They just depend on the realization.
Yeah, now you don't have any more. It's not even so.
Yeah,
you have the Voivovsky motifs.
Yeah, but I need to a realization into an abelian category. Yeah, so I have to use if S is not in characteristic 0, I will have to use one of the aladic. I will have to go into aladic perversions or aladic construction morphisms.
Okay.
Yeah, and then the result, I cannot prove it's independent of L. Of course, it should be, but I cannot prove it. Okay, so let's call that T1, and let's call that T2. Okay, and then that gives you two possible categories. Right? Constructible Nori motifs, which is the universal factorization of T1, and reverse Nori motifs, which is the universal factorization of T2. Which one should you use? So but it's not easy. So this is basically this is the graph. I mean, modulo the fact that we're using Wolfowski motifs as the diagram. This is the graph solution. This is the Nora solution. Okay, so the things. So you want to construct the operations. Okay, so operations you get for free. But the operations you get for free are the exact operations. Okay, so on the left-hand side, what you get for free is $2. Okay, so to get the operation for free, it needs to be defined on the diagram, but now you have a diagram where everything is defined. And it needs to be exact. Okay, so you get this one. Tensor product. In tensor product, you have to be a bit careful. You need to restrict the diagram, but okay, let's not worry about that. And I guess you get I or star. I is the closed version. And I think, yeah, that's it. On the right-hand side, what do you get for free? So you get $2 for F smooth. I mean, it should be shifted pullback, but if you have shifted pullback, you have pullback. You get so you get F lower star for F affine, whereas affine it. So this is a very fancy way to say what the two interesting cases are: finite morphisms and affine open immersions. Yeah, you get Gideon, you get external delta product, and you get nearby and vanishing cycles. And remember one thing. We want a two function from schemes or schemes of let's say varieties. Varieties of the key to like triangulated categories that sends S to this of n of S. Okay, so we want to make these Nori motifs. Actually, we want to make it into a two functor in several ways. Well, for example, if we use pullbacks, it's actually a contravariant two functor. But what I mean is, you need some non-trivial compatibilities on these operations. Okay. So a priori, this one. So on this side, you get it for free, function thing, because you have your pullbacks, they're exact. They're already, I mean, on this DM, they're already a two functor. All the compatibilities are going to go through. So it looks like this is the best choice. However, yeah. So what is missing here? Push forward. Okay. I mean, so when you start, yeah, it looks like this is the most reasonable choice. When you get all your pullbacks, everything works. You get all these compatibilities between pullbacks. I have no idea how to define push forwards. And there should be a right adjoint of pullbacks. I mean, you can just like go to the in categories, you get push forwards for free, but then you also want, I mean, okay. So if you go to some big categories, you just add enough colimits, limits, and all that, you're going to get push forward for free by the adjoint function theorem, but then you won't be able to prove that they are compatible with the basic realization. So you didn't win. Yeah. So if anybody has an idea how to define push forwards here. So the problem again, if you want to define a functor on these universal categories, it needs the only functors you know how to define are exact functors. How do you define push forward for chips? You go through some resolutions. For example, go to more resolutions. You leave the category of constructible chips when you do that. And if you leave the category of constructible sheet, you're kind of leaving this setting here. So I mean, if you ask me questions, it's a bit more complicated than that. But let's just say that I try to make motivic Godemont resolutions, and you can make the resolution, but you cannot use it. Well, okay. Now on the right hand side, yeah, I don't know how over time I am, but okay. So on the right, okay, so this one basically it's out because of that, as far as I'm concerned. Now the one here it looks even more hopeless because not only, I mean, okay, it looks like you have even fewer operations, and on top of that, you don't even have this two functor, right? Okay. So maybe I can maybe like 4 minutes. Yeah, okay, but I mean, I was told that an hour and a half is really the upper limit. So don't encourage me because I can go on all afternoon. Yeah. So maybe yeah. So the right hand side well somehow there was a path to something which surprises me, but okay. And what is the path is very twisted. So the first thing really is when the first you really want something like that. So you want to make pullbacks into a functor somehow, but you don't even have all pullbacks yet. So you have pullbacks for smooth morphism. So the first thing is you want pullbacks for closed inertias. Right? Because smooth morphisms, closed immersions, you basically get everything from that. Well, almost everything. If you work with quasi-projective varieties, you actually get everything. Which is why we work with quasi-projective varieties in the paper with Ibarra. This can be fixed later, but so how do you get I for star for I closed immersion? Well, so there are two things. You need to so if you want to construct a functor like that, you need to characterize it and then you need to construct it. So characterization is or like uniqueness is easy because it has to be it's a refrigerant of a functor that we know. And construction so I guess it's a slightly longer story, but the idea is very simple. It's like once you know the thing is unique, you can kind of do reductions. You can reduce to the affine case, for example. And in the affine case, and then you have this affine scheme, you have this closed subscheme, so it's defined by some number of equations. So you can do maybe an induction on a number of equations, and then you reduce to the case where you have nearby and vanishing cycles. And in that case, I upper star is given by an explicit complex using these nearby and vanishing cycles that are exact functors. And because they are exact functors, you have them for free. So I'm kind of lying to you. It's slightly more complicated, but it's the idea. And here, so you don't just write I upper star for a closed immersion, you want compatibility with composition. If I compose two closed immersions, I want the I upper stars to compose two. But this is going to come from this, right? Okay. The second part is pull-ups. So here, the idea is that you are doing these I upper stars and these F upper stars for F smooth. So the luck we had was that Ayub has a gluing theorem. Using a method of this. So it's like you have this category, you have two types of morphism. Every morphism is a composition of morphisms of these two types. I have a two-functor defined on one type, I have a two-functor defined on another type. When do they glue to a two-functor on the whole category? And there's a bunch of like diagrams and you have to prove they're commutative. Or like essentially commutative with compatibility. So he just gives you this blueprint and you have to check the properties, and we were able to check the properties. Although if you ask me which part makes me most nervous in this paper, that's that part. Right. But this is like only for triangulated calculators. So this is the reason that we wrote our paper in the triangulated setting, is that Ayub didn't do the infinity categorical gluing, and we didn't want to face that because you would have more compatibilities to check, a lot more. Yeah. And you would have to basically rewrite Ujang in this slightly different setting. No. Okay, but then you have pullbacks, you do push forwards. Okay, and how do you do push forwards? So it looks like you have the same problem as before, because even worse, because in the perverse setting, F lower star is not even a derived functor. It's neither left exact nor right exact. Okay. So the first thing is like, again, you have uniqueness. So uniqueness is like F. This should be right to right. This is F lower star. So if it exists, it's going to be unique. It's going to satisfy compatibility with composition. Okay. Now, so if you know perverse shapes, you know that push forwards are nice. In one case, the case of affine morphism. Because in the case of affine morphisms, they are right exact and they are derived functors. So then you have this f from x to y. So you reduce to x affine. And the first way we did that was to use a Chech covering. But you can actually be even more efficient. You use Johannes trick. The Johannes trick. I don't know if you've all seen Johannes trick. Right. So X is a quasi-projective scheme. It says that you have a an bundle over X that is an affine scheme. So you just replace X by this an bundle, and because of A1 homotopy invariance, which is kind of baked into the theory, that it just works. Yeah. And the last thing, once x is defined, I guess. So if x is defined, so you have x to y, x is defined. So now that means that f is going to factor as closed immersion times the second projection. This is just x being defined is a closed subscheme of some an. Right? I'm just doing this closed immersion times f. Okay? So this one you know how to treat. Right? So just now we reduce to this case. Okay, so now f is a projection of an cross y to y. And then reduce to n equals 1. Oh, well, you can do that, right? So now you have t1 plus y to y. Okay, and how do you do this one? By hand. So yeah, so this is where it gets really technical. So here, but look, what a pity! I'm out of time, so I cannot give you the really disgusting details. But as you asked me, I have them all. So what I can tell you, so you have to merge. So the idea is this Bennington lemma, as usual. So
2 or 3?
Hmm?
3-2 or 3?
I don't remember.
No.
So what Bennington's lemma tells you is that if you have a perverse sheaf on here, actually Bennington's lemma works for any affine morphism. But you have a perverse sheaf, then you can construct F lower star is cyclic resolution of this perverse sheaf using these very simple operations. So the first step is you're going to cut this by a hyperplane section, reduce to the complement, restrict to the complement, take extension by 0. Something like this. And Bennington's lemma tells you that if your hyperplane section is generic, this is going to be an acidic object and this is going to be a surjective map. Okay, and then you just repeat with the kernel, which has support a smaller dimension and all that. The problem, however, is that the hyperplane depends on the sheaf. So you cannot just apply Bennington's lemma straightforward. And not by the way, those are exact functors. So this is nice, but the exact functor that you use depends on the sheaf. So this is annoying. But the good thing is that you're staying in this category of constructible perverse sheaves, unlike the Godman resolution. Okay. So what we do, and the reason we have to restrict to A1 here is that we use kind of a universal version of Bennington's lemma on A1 cross Y. Okay. So what we really do is that we pull back the sheaves to A1 cross Y, do universal resolution there, push forward by the projection, and then do some kind of full die bisection and show that this gives the right result. But if you really want me to, I can write you 3 diagrams, but that's also kind of. Oh, okay. So the construction itself is not too difficult. What is less easy is showing that this is actually right adjoint to the pullback. Yeah, but maybe I've been tired your patience enough. So. Any questions?
So there's this Greek word by Stalinsky where he has a bunch of generators of DMS,
Yes.
kind of Lefschetz aeroplane guys.
Yeah.
How do they relate to that to me?
So Yeah, so I haven't talked about tensor products. And thank you, because I haven't attributed the results correctly. So maybe I can do that now. Yeah. So this kind of ideas is used in the construction of tensor products, but this construction of tensor products is not due to me, it's to look at Renzi. I should write his name on the board. So like 6 operations. Okay, so how does Luca Terenzi define tensor products? So what he proves. So you look at this category. So this subcategory is the category of robust motives, such that the first cohomology is concentrated in degree 0. Okay, so this is a little bit like what Ciesielski uses, and then this category is also a background for these Nori motifs. So that means I can define Nori motifs using this subcategory. So that means there are enough Voivodski motifs in this subcategory to generate everything automatically. Right? And the proof is also using this Beilinson lemma, it's ideas of the proof of Beilinson's basic lemma, which is you just if you start with something, then maybe if you do enough of these cutting by hyperplane sections, you can kill all the first cohomology except maybe 0. Is that?
Yeah.
Ciesielski, I don't know. So I read the paper. It was a couple of years ago. His work is he working with motifs over K or motifs?
Like over a general face.
Yeah, he does this kind of independence of L results, right? Using this.
Yeah.
Yeah. So so here the same techniques are used to define. Once you have this, on this external tensor product is just going to be external tensor product of Voivodski motifs.
Questions? Yes, I have a rather general one. It's a naive one, but for example, show motifs or other kind of motifs like those constructed by absolute homology, these kind of things. How do they sit in the features?
Okay, so Chow motifs. Do you want absolute or relative?
Absolute, for example.
Oh, sorry. I mean over K or over S.
Over K.
Okay, over K.
So just vary with the projector.
Yeah.
And some papers.
Okay, so the Chow motifs, so you have over K, so you have this category of Voivodski motifs. So Chow motifs here. So Chow motifs are a full subcategory here. They are the weight 0 objects in Mondaco's weight structure.
Okay.
So this is like your weight 0 objects. So, yeah, and the other, so this absolute yeah, I'm not sure about what. Okay, there is one category I
This the category of William varieties that I can one. I mean, the clock that I can close on William varieties.
I'm not sure.
Okay.
Yeah. There is one I didn't mention that is André motifs. You know André motifs. This is the one defined with motivated cycles. Characteristic zero.
Okay.
This one sits in Nori mode, it is the pure objects.
More questions? So can you show your the concept of universal Abraham contract?
Okay, thank you. Okay, where is this guy? You ask me.
I follow that really big.
Okay. So let's see. So yeah, I just need to draw a diagram. Diagrams take space. Don't worry. No. Okay. So you have this A1 plus Y, and you have this projection that you're trying to understand. So this is second projection. Okay. Okay, let's put A1 plus Y here. Let's put the same morphism. And here I have the section, the zero section, for example. No. And here, let's take A1 plus A1 plus Y. Here, I put second projection. Here I put first projection. So this is referring to the A1 factoring. Okay. And here, so this is U cross Y. So this is going to be the universal. So U is A1 plus A1 minus the diagonal. So the diagonal is going to be the universal hyperplane section. Okay. And here I have diagonal plus Y. So I call this J and I call this I. Okay, so this is the closed complement of this. Okay. And now, so the exhibition is that on like ordinary complexes, on Voivodski motifs, if you want. So this P lower star, sorry, it's not P, it's F here. So F lower star is going to be isomorphic to S upper star, Q1 lower star, Q2 upper star. So this is smooth base change. Because you do smooth base change here in this Cartesian diagram. Okay, or do you want me to detail that calculation or no? Okay. Yes, no. Because this is equal to let's see, F lower star, F upper star, S upper star. Because yeah, no, it's in the other direction. Damn it, I should not have tried to detail. Because F times S is a bit. But then this is just a base change map. In some direction. Probably that one too. Oh, okay. Okay, so you have this. So now this thing that you're trying to construct. So it's it should be the composition of these three functors. Okay, but in these two functors, this one and this one, they're already okay. Right? Because S is a closed immersion. So you know how to construct S. I mean, you know how to construct all the upper stars actually already. Okay, so you need to construct this one. Well, actually forget that I said this one is okay because we're not going to use that. So what you're actually going to construct is that one. but as just one factor. Okay, and so now the idea is thanks for the warning. So the idea is that the Bellisson's lemma will not give you an acyclic resolution that works for all sheaves. But what you can do is that for this Q1 lower star, you can have a resolution that works for every sheaf in the image of this function. Okay, and this resolution, I will just write it now. So the lemma is that for every previous sheaf on Y, so if we take L to be Q2 upper star of A shifted by 1, so this is a perverse sheaf. Okay, then you look at this. So I said our universal hyperplane is the diagonal. So I'm just doing this restriction to the complement of the diagonal, then push forward by extension by 0. And what I'm saying is that this is always exact. And these two are acyclic. Okay, so right. So it's just so this observation is just that this hyperplane section, it works for every sheaf that is pulled back by this Q2. Okay, so the reason we only do A1 is because for A1 you have a two-step resolution. I mean, maybe if you did AN, you could cook up a universal n-step resolution, but it would be awful. And why do it? We don't need to. Yeah. Oh, I should say also this. So this idea of using this diagram, we did not invent it. I learned it from a paper of Morihiko Saito, where Saito, he attributes it to Kashiwara. I don't know where Kashiwara got it. Maybe Kashiwara invented it. Yeah. So Saito, he also uses this kind of tricks with mixed large modules to construct the operations. And a lot of this paper is like an exercise in using the techniques of Bellis and Saito.